good morning learners. We are looking in this video at the Euclidean Geometry questions of the November 2016 paper, that is question 8, 9 and 10. Right, so we can start with question 8 that says, in the diagram below, PQRT is a cyclic quad, PQRT is a cyclic quad. Now, of a cyclic quad, one thing I know is that the exterior angle is equal to the opposite interior. And since I see the 70 there, I can somehow mark the 70 in here. And I also know that the opposite angles are supplementary for what it's worth. Having RT parallel to QP. RT parallel to QP, so from that I have that this angle here will be equal to that one, alternate angles, co-interior angles, things like that. The tangent at P, so since this is a tangent, you see tangent, the angle between a tangent and a chord is equal to the angle formed on that chord. So this one equal to that one as well. The tangent at P meets RT produced at S, RT produced at S, that tangent. QP is equal to QT, QP equal to QT, so those two angles will be equal. It's an isosceles triangle, and PTS is 70, PTS 70. Give a reason why P2 is equal to 70, that one there. P2 is 17. Okay. These two angles will be equal. So this one is equal to that one. At the moment, I can see that is 70. And the okay, right. Sorry. That one plus that one is going to be 180, right? Because it's opposite angles of a cyclic quad. And that one plus that one is also going to be 180 because of the parallel lines. So this one plus that 70 is 180, meaning basically this one is 110. And that one plus that one. So is then that is why P2 is 70. Okay, so I can start off by saying that the Q1 and 2 is 70. That was not given to me. I wrote that in. That's a 70. So I must first state here, question 8.1.1, that Q1 and 2 is 70. That was because of exterior angle of cyclic quad. This one is equal to that one, exterior angle of a cyclic quad, and then the Q1 and 2 plus the angle R would be 180, because it's co-interior angles in that parallel lines. Co-interior angles PQ and TR, parallel, which means if that's 70, that the R is going to be 110, right? And then I can say from that if the R is 110, that P2 is equal to 70 because it's opposite angles of a cyclic quad. Okay, calculate with reasons the size of Q1 and P1. Okay, so Q1, that angle there. Now, I mean, I can just use inside angles of a triangle because these are equal. That one is T2, 8.1.2a. T2 is also going to be 70 because its angles opposite equal sides. Please don't use isosceles. The angles opposite the equal sides of a triangle. There's a triangle. The angles that lies opposite the equal sides are equal. So I'm going to use this reason. T2 is 70. That means that Q1 is going to be 70 plus 70 is 140 plus 40. Q1 is going to be 40 by sum of angles in a triangle. And then question B, this one just wanted to know Q1, and then question B wants to know P1, that one, which I already said that this is going to be equal. So Q1 is 40. That also means that P1 is 40, and the reason for that is tan chord theorem. Tan chord theorem. Okay, because the angle between a tangent and a chord, that angle is equal to the angle formed on the chord subtended by the chord in the alternate segment, and I'm good. Question 8.2. A, B, and C are points on the circle having center at O. A, B, C points on the circle having a center at O. S and T are points on AC and AB respectively such that OS is perpendicular to AC and OT is perpendicular to AB. So those lines are perpendicular. AB is 40, that length there. AB is 40 and AC is 48. AC is 48. Right, now I see that first theorem that we learned in grade 11, that the line from the center of a circle to the midpoint of the chord is perpendicular to the chord. I see that theorem here. That theorem states that the line from the center of the circle to the midpoint of the chord will be perpendicular. So if it's the midpoint, then it's perpendicular. If it's perpendicular and I want to say this is the midpoint, or I want to say here, for instance, AT is 20 and TB is 20, I'm going to use converse of line from center of circle because I'm using the theorem backwards. The theorem says if it's the midpoint, then it's perpendicular. In this question, I'm using it's perpendicular, therefore that's the midpoint. So I'm using the theorem backwards. Calculate the length of AT. I can see already there the length of AT, 8.2.1. 8.2.1. AT is going to be 20. Is that centimeters? It's just 40 and 48, so units. Is 40 units, and I'm using converse of, and this makes it a long reason, converse of line from center of circle to midpoint of chord. It makes it a long reason, but rather write the reason, get the mark. Okay, so that's the length of AT, 8.2.1, 8.2.2. If OS is 7/15 of OT, calculate the radius OA of the circle. So OS, that length there, is 7/15 of OT. OT, I don't have the length of, but that's 7/15. That's 20, that's 24. I want to calculate the length of OA. Now in this question, let's make this OTX, right? Then that's going to be 7/15x, just to work with an x instead of the OT squared in Pythagoras. So in this triangle, I can work out OA by Pythagoras, but I'm going to have an x in it, right? So OA squared is going to be 20 squared plus x squared by Pythagoras, right? And in this triangle, I have OA squared is 24 and 7 over 15 squared. So OA squared is 24 squared plus 7 over 15x squared, also by Pythagoras. Right, in the two triangles, I must just actually first state where that 24 comes from. AS is 24 by converse of line from center of circle to midpoint of chord. You must actually just state first that AS is 24 before you use it, because it wasn't given to me, it was given to me the 48, but that one I used the theorem and I must first just state that. Alright, so now here I have OA squared is 20 squared plus x squared, and I have OA squared is 24 plus 7 over 15x squared. This is both OA squared, it's the same thing, so I can make these two things equal. I'm basically doing simultaneous equations. So I'm going to say 20 squared plus x squared is equal to 24 squared plus 7 over 15x squared, because they're both OA squared. 20 squared, 400, plus x squared is equal to 24 squared. 24 squared, which is 576, plus 7 over 15. 7 over 15 squared is I'm just going to keep it 49 over 225 is 15 squared 225. Just want to make double sure. Yes, x squared. Okay, and then let's just first add the like terms. So on this side I have x squared minus 49 over 225 x squared. If I take this over, and on this side I have 576 minus 400, and then 1 minus 49 over 225 is going to be I actually want it in fraction form rather. Let's just quickly say 225 minus 49, because this is 1 is 225 over 225, so 225 minus 49 is 176 over 225 x squared is then 176, and well, now I can actually take the 176 and divide it by 176 over 225 to get this on the other side. So take the 176 and divide it by 176 over 225. Nope, let's just try again. 176 divided by 176 over 225. I think it's just going to be 225. Yep. And then the square root of that was 15. So x is 15 units. Okay. So there we go. X is 15 units. Which is still not the length of the radius, that's just the length of the x. So if I look at the sketch, that is my x, which is 15 units. Okay, that's 15 units, and I still need the length of OA, which I can now, if x is 15, I can work out OA there. OA squared is going to be 20 squared plus 15 squared. So OA is going to be the square root of 20 squared plus 15 squared. It's 25. Okay, so there I have my radius, and that is question 8. Okay, we're going to move on to question 9 now. Okay. ABC is a tangent, ABC is a tangent. Now, if that's a tangent, that angle that's not a chord. So that angle, is equal to that angle, and this angle is equal to that one, which is x. So this, I can make x tan chord theorem. ABC is a tangent to the circle BFE, BFE at B. From C, a straight line is drawn parallel to BF. There I have the parallel line, which means I can use parallel lines, but I don't really see. Okay, parallel to BF to meet FE produced at D. FE produced at D. So there we go. EC and BD are drawn. EC and BD are drawn. E1 is equal to E2 is equal to X. I have that. C2 is equal to Y. Give a reason why each of the following is true. Oh, my phone is going crazy here. Sorry about that. Okay, give a reason why each of the following is true. B1 is equal to X. Okay, so B1 is equal to X because of tan chord theorem. I already said that actually. 9.1.1, I must just write it down. B1 is equal to X because of tan chord theorem. Right, that's 9.1.1. 9.1.2. Why is BCD equal to B1? BCD, this angle here, equal to B1. Well, that's B1, BCD. That's corresponding angles with these parallel lines, BF and CD. So B1 is equal to BCD because of corresponding angles BF parallel to CD. I suppose they're just helping me here to accomplish something later on. So this is X, and then that one there is also X. Right, because of corresponding angles, prove that BCDE is a cyclic quad. BCDE is a cyclic quad. I already said that that's equal to X. Well, that's given as X, and I just said this is equal to X. So you see the exterior angle equal to the opposite interior. They're actually helping you here. So I can just say here that 9.2 E1, which is X, is equal to C1 and 2, which is also equal to X from 9.1.2. Okay, and then if E1 and C1 and 2 is equal, that means a property of cyclic quadrilaterals hold up for this specific quadrilateral here, meaning that it's a cyclic quadrilateral because the property holds up. And then I'm using converse of. So I can say then that BCDE is a cyclic quad, and my reason for that is going to be converse of exterior angle of cyclic quad. Okay, 9.3. With which two other angles are also equal to X? I have this one X here, and that one B1 I already showed. Well, this one will be equal to that one then if this is a cyclic quad, so I can say D2 is equal to X. D2 is equal to x because angles in same segment, and I'm using the cyclic quad BCDE. I'm just mentioning it for the person marking my work, so that's also equal to x. And then maybe parallel lines might help me here. I already said C1 and 2 is equal to x. And that one will be equal to that one, but it's not necessarily x. That one is x. That one, EC is not a tangent as far as I know, so that I can use maybe tan chord theorem. I have a feeling that it should be this one. Just B2 and 3 there. I'm just quickly checking. I wonder how many of you have already gotten this now, and whether I should maybe edit this out, this long break that I'm taking here. I have that one is x. That one is x, meaning that one is x. That angle there, but I think that this is now becoming a bit difficult to do, but you see this angle E3 there is 180 minus 2x, right? So there's a x and a x, so this angle E3 is 180 minus 2x. I think I'm taking a longer route. Some of you might have seen something easier. If you see something easier, please share it with us in the comments. So I see there that one is 180 minus 2x because of the 2x's there in on a straight line, x and x. So E3 is, I'm going to write this down as I say this. So E3 is 180 minus 2x because of angles on a straight line, right? Then in this cyclic quad, that angle is equal to that one. So B4 is also 180 minus 2x. B4 is also 180 minus 2x because they're angles in the same segment, and then since that's x and x is also going to make that angle then equal to x, b2 and 3, because this is 180 minus 2x, so 180 minus x is a straight line again. So since b4 is 180 minus 2x, that makes b2 and 3 equal to x because angles on a straight line. If you take let me just show you a bit more clearly maybe what I mean by that. B1, 2, and 3, B1, 2, 3, and 4 should be 180, right? Angles on a straight line. So B1 is x plus B2 and 3 plus B4, which I said is 180 minus 2x. Should be 180 because of angles on a straight line, and then x minus 2x is negative x plus b2 and 3 together, x minus 2x, b2 and 3, and then 180 minus 180 is 0. So if I take the x over, you see b2 and 3 is equal to x because of angles on a straight line. So there b2 and 3 is x. But I think there might be something easier. I'm not sure. Okay. So I have B2 and 3 as x, and I have D as x, two other angles that are equal to x. So I have that. Is there maybe somebody who has something else? Right. Because we already have this one, B1 is x. We already have BCD, which is x. I can't mention that again. And those two are x. So that, and that I already have. This one is equal to that one, but that's not x. Right, B4, B3 and 4 is equal to f, but it's not necessarily equal to x. And I now said that one is equal to x because of angles in the same segment, but then I need another angle here. So the one that I see is B2 and 3 together, but there's maybe an easier way to prove than the way that I did here. Okay. So prove that B2 is equal to C1. So I want to prove that B2, this one here, is equal to C1, this one there. Now, since C1 and 2 is X, and that's a Y, also angles in the same segment make this a Y. You see this 2 together is X, and that's a Y. This 2 together is X, and that's a Y. That's going to make these two equal. But now to write it down, I can write down that C1 is equal to x minus y. Can you see that? The big angle is x and that small angle is y. So C1, 9.4, C1 is equal to x minus y. Well, that's C1 and 2 is x. I already said that somewhere. C1 and 2 is x. C1 and 2 is x and C2 is y. That's pretty obvious. I don't really need a reason. And then I must just state that B3 is also y. So B3 is equal to y by angles in the same segment. That's also in the quad BCDE that I'm working with from earlier, that quad that I proved. So B3 is y, which also means, since I said B2 and 3 is x already there, B2 and 3 is x from 9.3, then and B3 is y, that means that B2 is also x minus y. So since B2 and 3 is x and that part is y, then that angle is also x minus y. And since C1 is x minus y and B2 is x minus y, that proves that B2 and C1 is equal. So that means that B2 is equal to C1 if you see they are both x minus y. Okay, so that's question 9. Then I have question 10 left to do. In the diagram, triangle PQR is drawn. S and T are points on the sides PQ and PR respectively such that ST is perpendicular to and parallel to QR. Prove the theorem that states that PS over SQ will be equal to PT over TR. This is the proof of the proportion theorem. Which is an examinable proof. I'm quickly going to do it. Most of you should know how to do it by now already, but let me just quickly run through it. So I'm going to construct my two diameters there of this bottom one. In the top one, I must construct two perpendicular from that point perpendicular to that line, the height. Let me call this height K, H. And then from that point perpendicular to that line, you must actually please use a ruler and not like me here with free hand. Let's call this line here K. Right, and I'm just going to also put in A and B there, just so I can say SA is equal to K, just to make it clear which one is which, and TB or BT is equal to H. Right, the perpendicular height there. Prove the theorem that states PS over SQ. So, I'm going to start here with, let me somewhere write it here on this area here. So, I'm going to start with the area of triangle. I'm going to first work with QTS and PST. So the area of triangle PST over the area of triangle SQT. SQT is going to be, area is half base times perpendicular height. So of this triangle, half base PS times perpendicular height H. Half base PS times perpendicular height H. And this triangle, half base SQ, half base SQ times, and the perpendicular height of this triangle is also that H. I'll quickly just try and explain that. Let me just quickly turn this around. If I'm looking here at this triangle there, this one, extend the baseline, and then from its highest point, there's the highest point, there's my base. If I drop down a line perpendicular on the extended base, you see this, although the height is outside, if I go from the base there perpendicular up to the highest point, it's going to be that height, you see. So sometimes the height can be outside of the triangle. If I look at this triangle there, from the height, drop it down perpendicular to the base, I just extend the base. So you see this height is actually the height of this triangle and the height of this triangle. So I use the same height there. Okay, and then that will cancel, so I only have PS over SQ. Okay, and then on the other side I'm going to do exactly the same thing. So I'm taking the area of PST, area of triangle PST, again same thing, but now I'm taking SRT, that triangle there, SRT, area of triangle SRT is equal to, and now I'm using this as my base and my perpendicular height, so that this triangle here, you see from its highest point, if I drop down a line perpendicular to the extended base, again this height here is the height of that triangle and of this triangle there, which is K. That's the AS is the line K. Okay, so the height K. So there I'm using now PT of this triangle as the base, half base PT times perpendicular height K. If I use this as the base, I must use the line that's perpendicular to that as my height. If I use this as the base, I use the line that's perpendicular to that. I can use any line of a triangle as the base as long as the line that I'm using as the height must be perpendicular to the side of the triangle that I use as my base. Okay, so when I use this as the base PS, I use that as the height. When I use PT as the base, I use that as the height. Okay, and then SRT, the base RT of RT times perpendicular height K. And yet again, that cancels, leaving me PT over RT, PT over RT. PT over RT, which I'm just going to write as TR, because if I look at that, I want to show PT over TR is equal to PS over SQ. Right, so now I want to show that these two are equal. So I want to show that these two are equal. Now PST, area of PST is naturally going to be equal to area of PST. It's the same thing. I must just show that the area of triangle SQT is equal to the area of triangle SRT. And if I look at SQT, which is this triangle here, and this triangle here, you see they share that base. Both of them, if I look at this, then the perpendicular height from there, if I use this as the base for both these triangles, because they both lie on there, the perpendicular height from the base to the highest point is going to be the same because it's parallel lines. So the perpendicular height there to that and there to that is going to be the same because it's parallel lines and the distance is the same. So it's going to be the same because they have the same base, ST, and the same height, which lies between, and a height that lies between parallel lines. So the height is going to be the same naturally. And then since this is equal to that and SQ is equal to SRT, this is exactly the same as that. So then I can say PS over SQ is going to be equal to PT over TR, and that's the proof of this theorem, right? And then 10.2, let's finish off with this question. It says, in the diagram HLKF, HLKF is a cyclic quadrilateral. Okay, I can see that. The chords HL and FK are produced to meet at M. The line through F parallel to KL, the line through F parallel to KL, there we are, meets MH produced at G, MH produced at G. So there's a set of parallel lines, which means I can use my proportion theorem because there's a triangle with a set of parallel lines. MK is X, KF is 2X, ML is Y, and LH is equal to HG. So if there's parallel lines in a triangle that's X and 2X, I can see the ratio is 1 to 2. So if that's Y, can you see that this part is going to be 2Y, and since they give me that is the same, that's also going to be Y and Y. 2Y is Y plus Y, and that's the same. Okay, so without even looking at the question, I can already assume that. Let's look at the question. Give a reason why GFM, this angle there, GFM, F1 and 2, is equal to LKM. LKM, this angle there. I mean, well, there's my parallel lines, and those are obviously corresponding angles. So 10.2.1, it's because it's corresponding angles. Okay, 10.2.2, prove that GH is equal to y, gh is equal to y. I already told you that's going to happen, but let's now see how to write that down. So I can say mk to kf, mk to kf, and you can write it as a fraction or a mk to kf is equal to ml to lg is equal to 1 to 2. You can write it as ratios like that, or you can write it mk to kf is equal to ml to lg like that, because of proportion theorem. And whenever you use the proportion theorem, please just state your parallel lines KLFG that you are working with in the question, and then I can see MK is X, KF is 2X, ML is Y over LG. So the X's can cancel, leaving me 1 over 2 is Y over LG, meaning that LG times 1 is equal to 2 times Y. So LG is 2Y, okay, by prop theorem. And then since LG consists of LH and HG, which is equal, LG is LH is equal to HG, meaning Y is equal to Y, to make 2Y. That was given to me to make the 2Y. I can say then, okay, GH or HG, GH is Y. Okay, 10.2.2, that was number A. Now next I want to do number B. Triangle MFH. MFH, it's this triangle there, is similar to MGF. MGF. So this triangle here is similar to the big triangle there. Okay, now to do similarity, I'm immediately searching for equal angles, and in MFH, I immediately notice the angle M in MFH and MGF, same angle. And I need to decide always when doing a similarity proof, I can start by saying M is equal to M because it's a common angle in both triangles, but I also need to decide I'm doing let me somewhat take this smaller triangle on the left hand side and then the big triangle on the right hand side. So all of the angles that lies in this one I'm going to list on this side, and the big one I'm going to list on the other side. Just makes my organizing a bit more strategic and structured. So now I'm looking for a reason why h1 and 2 is maybe equal to that, or this angle is equal to that angle. MFH, I'm looking for this angle is already equal. So now I'm looking for this angle in the big triangle. This angle is not going to be equal to that one. You can see that. So obviously I'm looking for F2 to be equal to that angle G. All right, now I can see that F2 plus L2 is going to be 180 because it's opposite angles of a cyclic quad, and there's parallel lines, so this one plus that one is also 180. So this one plus that one is 180, and also plus that one is 180 by co-interior angles. So I can use that. I'm going to say L2 plus F2, and F2 is in this triangle, so I want to have F2 on this side. So F2 plus L2 is equal to 180 because it's opposite angles of a cyclic quad. Then so okay, I want to have the F2. The L2 is just a midway angle that I use. It's not part of the two triangles that I'm working with. So I want the F2 in this triangle. And on the other triangle, I want the G. So I'm going to put that on this side. So I'm going to write it like this. 180 is equal to L2 plus G. Okay, and you see the L2 and the 180, it's the same, and the G. Right, I just swapped them so that I can clearly have the, I'll show you now. Okay, so then this is L2 and G is 180 because of co-interior angles, KL and GF, KL parallel to GF. So if I have something plus L2 is 180 and something plus L2 is 180, those two somethings naturally must be equal. So I have F2 is equal to G. But the reason why I wrote it like this, with the 1 is equal to 180 and 180 is equal, because I want the F2 on this side and the G on that side, so that my angle from this small triangle and big triangle are on the left hand side and right hand side respectively. So F2 is G, and then in this triangle I now have M and F2, and the other triangle, that's the other angle that's left, is H1 and 2. So on the left hand side, H1 and 2 is equal to, in the big triangle I have M and G. I have M and G, and what is left in the big triangle is F1 and 2. So H1 and 2 is equal to F1 and 2, and those are just because it's the third angles of the triangles. You actually, when you do the similarity proof, just need to actually prove two angles. The third one by default will be equal, and then I can say, so triangle MFH. And you see, if I follow the L is just a midway point that I used. So if I look at the angles MFH, MFH is similar to triangle ML. ML is a midway point, MGF. MGF by angle, angle, angle. Okay, and then they want me to show that GF over FH is equal to 3x over 2y. GF over FH. So I'm going to obviously start writing down. This is very typical after a similarity proof. What I'm going to do is write down that MF over MG is equal to FH over GF. FH over GF is equal to MH over MF, MH over MF, and what they want me to show here is GF over FH, GF over FH. It's that one, but it's the wrong way around. That doesn't matter. Is 3x over 2y. So I'm looking at the MF and the MG. MF is 3x and MG is 3y. MFMG is 3x over 3y, and I want to have it as 3x and 2y. That's weird. Let's look at this one, MH and MF. MH is 2y and MF is 3x. Oh, so this one, MH and MF. Okay, so, and they actually want GF over FH, the reciprocal of this. So I'm just going to write, let me just write my reason first. From similarity. So I'm just going to write the reciprocal of this. GF over FH is equal to MF over MH. I just did the reciprocals of both. And I want to show that GF over FH is equal to, and MF on the sketch, MF you see is x and 2x, which is 3x, over, and MH is ML, LH is Y and Y. So you see that, and I already stated those Y's earlier, so it's not necessary there. LH, HG, Y, Y. I already stated that. So I can just say 2Y, and that is what I want to show here. And then lastly, 10.2.3, we're almost at the end. 10.2.3, show that y over x is root 3 over 2. So I'm assuming I'm going to use this fact that GF over FH is equal to 3x over 2y and try and get y over x alone here, but GF over FH is also and also GF over FH is equal to mg over mf, which is equal to mg is 3y, y and y and y, so mg is 3y over fh, mg over mf. mg is 3y, mf is 3x over 3x. And what I sit with here now is that gf over fh is equal to this and this. That can cancel. So it's equal to 3x over 2y, but it's also equal to y over x, which seems weird, but let's quickly make this equal and see where that leads. So I have from this, because both this is the same, that 3x over 2y is equal to y over x. Cross multiply, I have 2y squared is equal to 3x squared. And what I want to get alone here, I'm just going to have to work on a new page now. Let me just turn the page around quickly and rewrite this. I have 2y squared is 3x squared. So I have 2y squared is 3x squared. From cross multiplying there, 3x squared to y squared. Okay. And what I want to have here is what I'm aiming to get to. Just try and refocus the camera quickly. Okay, so what I'm trying to get here is y over x alone. So I don't want the 2 there. I'm going to divide it out. So I have y squared is 3 over 2x squared. And I want to have y over x. So let's divide the x. Y squared over x squared is then 3 over 2. And to get this y over x, I'm going to take the square root. So y over x is equal to the square root of 3 over 2. And that is exactly what I want to come to. Cool. Okay, that wasn't too difficult. And this is the last question here. Boys and girls, I hope you're really trying your level best with the Euclidean and you're really improving day by day. The only way to really master Euclidean is you must practice, practice, practice. And I hope this video have been helpful for you.